So, welcome to Introduction to the Lattice Boltzmann method in winter term 2023 and 24. This is an introductional lecture to the Lattice Boltzmann method. What we will do today is not so much related to the Lattice Boltzmann method specifically, but more about the background behind it, which is kinetic theory. So actually today will be pretty theoretic, but the thing that I want to avoid is that stuff comes out completely out of the blue. So what we are trying to do here is get an understanding where things are coming from. It will, in later lectures, become more practically relevant. But I have a teaser for you anyway. If we go to the web page of our institute, and then there is a division, Kinetic Fluid Dynamics, and in this division, Kinetic Fluid Dynamics, you will find the link to something that's called FlowSimGS. So take this as a teaser. We can click on this, and then in your web browser starts a simulation using the Lattice Boltzmann method. So now this is running in your web browser. Actually, it is running on the graphics card of your computer, to be more specific. This is a tool that was actually completely implemented by a student of ours, and so he spent a lot of effort designing the interface, where I have nothing to do with the interface. So he did here a pretty good job on this. We're not going to talk about interfaces, of course, but the theory behind the method is something. So what he has implemented here from a theoretical point of view or from a numerical point of view, this is the level of what you learn in this lecture. So in the end of the lecture, you should be able to implement something like this. And actually, this is kind of also kind of will be your homework. Yeah. So as a homework, you get to implement a small example and measure some track. So what we see here actually is a visualization of the track, the force acting on the roof of a building. So this was a civil engineering project. So this is why it looks like a building, but could be anything else. Here in this, we can actually move this. The red line, again, as I said, is displaying the force that we see, and we can here do funny changes. For example, we can display the curl of we can have the velocity. This is what we started off, the velocity in a certain direction. What is stated here is D is the density, which is in Lattice Boltzmann related to the pressure, which is something that we are going to learn during our lecture. Okay, so please have a look into this. I put the link specifically to this small tool in here, so that you can take it and have a look. Okay, so this was the teaser. Now, what we are talking about today is the Boltzmann transport equation, collision integral, conserved quantities, and something that's called the H-Theorem. And maybe this is a kind of maybe some students from previous year told you this is very complicated because you get the H-Theorem. But the H-Theorem is a very interesting thing about nature. So even if it may not become completely clear right now what it means, and looks a little bit complicated with all these integrals. Yeah, it's just a very interesting result of nature that you should get an idea about. Yeah, it's not extremely important for later understanding the Lattice-Boltzmann methods, but it's very interesting. So then this is why I put this in this lecture. So, and I have this teaser here with the three different ways to regard the world. Yeah, so there is an atomistic, a kinetic, and a continuous. Yeah, and now we start with our lecture. There's the three different. I'll say, okay, I write it. Sorry, I write it a little bit simpler. Three ways to see the world, or to describe the world, trying to understand the world. So, the first is actually the one that came from a physical point of view. I mean, from a historical point of view in physics, comes a little later, but is now absolutely accepted, is an atomistic view of the world, right? So you know there are particles down there. These particles have a mass, and there are many. This is why there is an MI, so mass of particle I, and this particle has an acceleration, also associated with this particular particle, yeah, or atom or molecule, and this will change according to forces F, I, and J when we sum over J. So what does it mean? So we have a particle or atom or molecule right here, right? So, and say this is and we have another one there, and we have one there, and we have one there, and usually we have many, right? And now I draw only 4, yeah? So say this is, and all the important thing, all these are individuals, yeah? So there's a particle called 1, there's one 2, there's one 3, and there is one called 4. And now they are acting forces somehow, yeah, van der Waals forces, whatever. So they act in between all these particles somehow. And as you see, this is why I draw only 4. There are many, yeah, forces now acting between them, yeah, because they have all that amount of the number of neighbors. So what the forces do is they exchange momentum. So there's an exchange of momentum. You know, when you come from, did you learn, I mean, we all learn Newtonian mechanics. This is actually what is also written here. But if you learn, for example, Hamiltonian dynamics, you get a different view of forces. So here, actually, what forces are fluxes of momentum. Yeah, momentum flows from one particle to another particle. Yeah, this is what is happening here. So between all particles, there is a flux of momentum somehow. So the entire thing here is governed by forces between particles. And I mean, sometimes I had a recording of a lecture, and there was a leaf blower in front of my window. Yes, this was completely ruined. Okay, so what is important to notice here is that these particles are distinct. This is in particular important from a practical point of view. They are distinct and they follow, you could say, Newton's laws. So Newton's laws is pretty simple. What is interesting, to know, because I used to say there is a Newtonian point of view. In a previous year, then I held this lecture, but I came to the conclusion that this is probably a little bit confusing, because Newton himself did not believe in atoms. Yeah, so this atoms came much later. So he was concerned with big bodies, planets. Yeah, there's forces between planets or something like this, or an apple, for example, but not atoms. But actually, these atoms behave according to Newton's laws. And there are distinct features, like distinct apples, distinct planets. Okay, distinct entities, not features. So there is a continuous view of the world, and this is related to the Navier-Stokes equation when we talk about fluids. So continuous is generic, and Navier-Stokes equation is specific for flowing matter, fluids. Yeah. You heard about the Navier-Stokes equation? Yes. You also probably learned it. So there's a time derivative of something that we call u, which will associate with which is the velocity, and then there is a material derivative. I mean, combined, there's a material derivative. Say this together is the material derivative, which I hope you've learned already. Yes, okay. And then there is a potential term. And this is, so to speak, the pressure potential. And then there comes a diffusion term that we call this. So there's a Laplace operator, and this is diffusion. So, and then this is usually combined with a continuity equation. So there is a density, rho, and this density is, the time change in the density is equal to minus the divergence of the velocity field scaled by the density. So this is actually where the continuous approach gets its name to, because this is the continuity equation. Okay, so you are familiar with this. This is how fluid dynamics is usually done. So a fluid, say, a fluid is, and now this is important, is a continuous field. So this is what is a fluid, it's continuous. Yeah? Continuous field, and this is still obeying conservation laws, which are somehow enshrined in the Navier-Stokes equation, obeying conservation. So they will always conserve mass, momentum, energy, and what else? There's one thing that everybody forgets. State equation. Okay, no, this is not related to the state equation is not a conservation law. This has a we are now talking about what is conserved. You know, energy, the thing with energy is that the Navier-Stokes equation in this form does not conserve energy. If you want to conserve energy, you have to add an energy equation. Yeah? So I put energy, you know, because it's... What was this?
Energy potential is conserved.
What is energy potential? The potential energy.
Yeah, gravitational potential.
No, that is not conserved. No, this is actually not conserved because this can be turned in another. I mean, this obviously the Navier-Stokes equation would allow you to drop something, and then it would go into kinetic energy. Yeah. So and then the energy would be dissipated. This is the reason why it's not energy conserving. They would be dissipated by this term, and this term would have to be coupled to an energy equation as a source term, which increases the temperature when there is friction. So diffusion generates friction, and the friction would generate heat, and then the entire thing would be conserved. Yeah, but since we did not write an energy equation, I put energy here in brackets because it's not actually conserved here, but something that is conserved kind of implicitly is the angular momentum. Yeah, angular momentum is conserved. So, the Navier-Stokes equation is older than the atomistic worldview, unless you're talking about the ideas of the ancient Greek people. So there is historically this is pretty interesting, because the atomistic worldview was always present, has never completely disappeared, but was considered to be something like, you know, like a flat Earth theory would be today, right? So this is something that 3,000 years ago, some Greek scholars thought that there were atoms, and now we know better, right? So it never disappeared completely, and it was only in the 19th century that it gained momentum, and it was accepted in physics in the 20th century only. So it is absolutely recent, actually. And the Navier-Stokes equation is a century older. And I mean, kind of the reason. So there was this, you know, there once was a considerable fight between the atomistic guys and the continuous guys, and the continuous guys had to their advantage that they had all these that they all had all these differential equations, partial differential or other, that actually gave correct results. And they would always argue, okay, we have the correct results. So the and what is with the atomistic view? It doesn't tell us anything. Now, from hindsight, you know, it's kind of surprising that nowadays we accept the atomistic view. Everybody of us accepts the atomistic view, and at the same time you're using partial differential equation, right? And there is a cognitive dissonance, in a sense, between them, if you think about it, because what a partial differential equation obviously does, it is assumes in continuum, because if you take a derivative, you're assuming a continuum, otherwise, but there is no continuum. Yeah? Now you believe in both things at the same time, so how comes? Do you have did this ever occur to you that there's something fishy? Yeah? So, and now what comes into play is what was developed in the late 19th century and then finalized in the 20th century only, is the kinetic theory, physical kinetics. And the thing which is very annoying is that the word kinetic has at least 5 incompatible meanings. This is why I have to focus a little bit on this, otherwise you are getting completely confused. So you learned, certainly you had technical mechanics or something like this, and there they will tell you that kinetics is the relation between forces and the change of momentum, right? This is what they tell you is kinetics. And mechanics is of course part of physics, so okay, so this is kind of physical kinetic. There's biological kinetic, there's chemical kinetic and other things too, but they are in a different domain. But then there is something else in physics that's called kinetic, and is actually called if you look at the textbooks, it's then called physical kinetic. So there's kind of the most important series of textbooks for physics students is the Landau-Lifshitz. Yeah, you heard about them. So there are 11 volumes. The first one is mechanics, and the 11th is called physical kinetics. It's twice the size, twice as many pages as the mechanics. The mechanics is, so to speak, the start of what a physics student should know, and most engineers, stop after probably volume 3 or so, and physical kinetics is more or less the end. So physical kinetics is going back to Boltzmann, and is the foundation of where also Lattice Boltzmann is built on. So this is reason enough why we have to discuss this. But the other thing about this is this overcomes this cognitive dissonance between, on one hand, we have atoms, and on the other hand, we have a continuum. So the physical kinetics give you the answer why you can describe the universe and under what circumstances you can describe the universe with differential equations, the differential equations that were known already before we know about atoms, and on the same side, in the same time, accepting the atomistic view. So this all goes down to what Boltzmann derived with the so-called Boltzmann transport equation. So the Boltzmann transport equation is kind of the thing where Lattice Boltzmann is later coming from, but it's completely a research topic in its own right. Yeah. So because Lattice Boltzmann is kind of engineering, yeah, and this here is physics. Yeah, really physics. So the Boltzmann transport equation, in a sense, describes the same thing as the Navier-Stokes equation, which we'll see in a later lecture, I believe in lecture 3, I guess. And this but this uses different variables. Instead of the velocity and the pressure, we have this function f, which is the probability of finding a particle in a certain the probability density function to find a particle in a certain position and at a certain velocity. So this also has an advection operator. The advection operator is similar but different from the operator in the Navier-Stokes equation. So instead of having the velocity u here, we have another thing This is the velocity c. Sorry for the Greek letters that are used here. Boltzmann used a lot of Greek letters. So this is a microscopic velocity c, and this is transporting this probability density function. Then there is a term we are not talking too much about. There's a long-range forcing term that goes into velocity gradient operator. So the nabla is the derivatives in space, obviously, this is what you know, but you can also take a derivative according to velocity. Yeah, so this is what is in this term. Don't get nervous about this. This is just for completeness. And then on the other side, we have something we call omega, which is a collision operator. Now, what is the bottom line about this? Though, in comparison to the atomistic view, yeah, now we accept there are atoms, and the difference between the atomistic view and this kinetic view is that even though we accept that there are atoms, we do not look at the individual atoms. So, but we only take a statistic, yeah? We take a probability for one particle being there, for a particle being there or not. And we do not care which particle this is. So now comes the, from an information point of view, important distinction, namely, a distinction. The distinction here is that it's undistinguishable. I mean, you have to understand this a little bit like this. When we model, we want to reduce the amount of information that we are dealing with to a minimum, yeah, that still describes our system. Because otherwise we need to be God, obviously. You need to know everything. Now, in the atomistic view of the world, where every particle is one individual, you deal with a lot of information that you don't need to track when you're in the continuum. So the continuum deals with much less information than the atomistic view of the world. Now we want to take both into consideration, yeah. So we want to see, the big picture, and also accept that down there are atoms. How can we do this? We can do this by no longer distinguishing between our particles. So the difference is, you see, the students in your class, yeah, say there is one called Mark and one called Peter, and who was there? Mark and Peter, and Anna was not there, and so on, yeah? Now, forget their names and say there were 3 students, there were 5 students, yeah? And so you could also say, okay, there are 10 by the power of 23 particles. And now this makes the difference. The atomistic view, if you want to describe a big system, you have to describe the positions of all these particles. And now you just say, okay, there are so and so many. And otherwise you don't care. You may be caring for, okay, so one part, so there are 2 kinds. For example, there's oxygen and nitrogen. Yeah? So, okay, 2 kinds. So you can distinguish between them, but all the oxygens are the same and all the nitrogens are the same. And you don't care any further. So now this makes the difference. F, as I said, is the probability density. As the probability density of finding a particle in 7D phase space. So phase space is a space where you could say this is a state space. So, for example, the state space in this lecture room here would be, for example, the seats. Yeah, and now you are in a particular seat. Yeah, so you could go into another seat, then you would change your phase space. Yeah, so this is more or less the idea behind this. So in phase space. So why is it 7-dimensional? It has time. So at a certain time t, at a location, say we call this R. So my R's and my V's are indistinguishable. I'm sorry. Yeah, I try to always mention this is an R. So R is composed of X, Y, and Z. And then there is speed, molecular speed, xi, and now we write this as xi and as, now this is difficult to write letters, this is upsilon, small epsilon, and zeta. Okay, maybe I don't know whether students run away because we are using this, because Boltzmann used Greek letters. We could, yeah, but I think we can manage, right? Should be possible. So what we do here in physical kinetics is we regard particle statistics instead of individual particles. And with this, we reduce the information in a similar way as if we went to a continuum. And in all actuality, I mean, the Boltzmann transport equation is a partial differential equation, obviously. Yeah. So actually, F is continuous because it's a probability. Yeah. So now with this, we went from the individual particles already to a continuum, and the difference that we made here is that in the atomistic view, a particle has a certain velocity, whereas in this view, a particle is at a certain velocity. Yeah? So we turn this around. Yeah? Like this velocity has a particle. Like I could say you are sitting there, or I could say this chair has you, right? This is the difference. And this also makes the difference. So let's look at all these terms. It's doing okay, half time already. So we have the time derivative. Obviously, this is the change in time. Then we have the advection operator, which is distinctly different from the one in the Navier-Stokes equation. You can think about why and what is the big difference. And there is the forcing term. So the forcing term is, this is basically related to large range forces. Okay, so it's not, this is not related to the forces that we usually have in when we do like molecular dynamics. Then we have, van der Waals forces, particles coming close to each other, and do things with each other. So these are forces that come from the outside, so to speak, like the gravitational force, or if you have charged particles, electrical forces. Yeah. So most of the time we'll ignore this thing. Yeah. This is not a very important thing. And now we have here the collision on the other side. So this collision, this is what in the atomistic view would be related to some, intermolecular forces. So they are the short range forces. Okay. Now the advection. Now, I gave you some time thinking about what is the difference between advection in the kinetic and in the continuous, so in the Boltzmann equation, in the Navier-Stokes equation. So here we regard a particle that starts at a time t at a location r. So this is an r, yeah? It's always I'm sorry for my bad handwriting. And now this will move, of course, according to the velocity in which it is. Yeah, it does not have a velocity, but it is in a velocity. This is the way of thinking. So it will change its position to r plus dr. So small change at taking its time t plus delta t. And now the microscopic velocity is nothing else than the derivative of its position by time, which is of course something that you know, right? Just particles. So particles move in the direction of their velocity. And this velocity is called xi. So now this xi we'll call this microscopic velocity, and this is different from the macroscopic velocity in the Navier-Stokes equation. So how is it different? Let's have a look at the Navier-Stokes equation. So in the Navier-Stokes equation, the advection operator is dt. So I'm using this shorthand, but I believe you understand what I mean. dt of u, and u is advected with itself. u dot nabla u, yeah? So this you have seen, this is the advection operator in the Navier-Stokes equation. In the BTE, Boltzmann transport equation, we are advecting a distribution which is the dependent variable. Here, of course, in the Navier-Stokes equation, obviously u is the dependent variable, right? So the one we are solving for. In the Boltzmann transport equation, we are solving for f, yeah? And this goes to xi. So this part looks a little bit similar, but okay, I'm writing you. This is of course nonsense. I mean, it's advecting the probability, right? So now in both cases, u and f are independent variables. So these are the things we are solving for. Okay, you're familiar what I mean with independent and dependent variables? Okay, apparently, sorry. You are familiar what I mean with dependent and independent variables in a partial differential equation. So the dependent variable is the one that I take the derivative with respect to the independent variable. Yeah? The important thing here is that xi is an independent variable. There's a coordinate in our system. So what does this mean? This means that in the Navier-Stokes equation, we have a nonlinear advection operator. Right? So because it depends somehow, so it's not just the square, it's even more complicated, right? But it depends on a strange squarish-like combination of the solution, right? Whereas in the Boltzmann transport equation, the advection is linear. Yeah, because it does not, it depends only linear in the solution. Now comes the question, does this look more or less difficult to solve? Because sometimes, I mean, everybody is solving the Navier-Stokes equation because they think it's easier. Okay, we are, let me see, okay, half time. Okay, very important to understand this. So the Navier-Stokes equation obviously has no collision term. So this is something that's a little bit new here. It's actually related, the funny thing is related to the viscosity actually, which is something that we get in a later lecture. We don't come to this today. So we have an assumption, or Boltzmann has an assumption. So he assumed that there is only binary collisions. Meaning that whenever particles touch, only two of them are involved, never three at the same time. Huh? This is, collisions are in a sense, not so common that it is, so, because when collisions are not, when two people meeting is not very common, then three people meeting is very uncommon, right? You're walking through the desert and sometimes you meet somebody, but that three at the same time meet is unlikely. So we are just dealing with two particle collisions. So we now, there's an interesting fact about two particle collisions. When two particles collide, they will always be in a plane. So they come in and they go out, and this will happen in a certain plane because there's 3 dimensions but only 2 particles. So we can always draw this into one plane. Of course, for different collisions, the plane is not the same. That's an important thing. But for one collision, they will always happen in a plane. So let's take our velocity field now. So when particles collide, we do not care about their position, obviously, because they collide, they are in the same place, right? Otherwise, they wouldn't collide. So say this here is my coordinate, velocity coordinate xi, and this here is my coordinate upsilon. Then I can regard a collision, so there is 2 particles coming in. I call this here xi1, the first particle coming in, and I have a xi2 particle, the second particle going in. They collide, and then they will exchange momentum between each other and go out in a different way, which we could, for example, draw like this. Xi1, and the result of this I indicate by this by this dash xi1, and say this here is C2 dash. So now you see they come from the left and they somehow go out to the right. Probably I've not drawn it completely momentum conserving in this picture. Yeah, I'm sorry for this. This is difficult to do. Therefore, we'll change this this to a little bit a different picture. I wanted to indicate this, that this would be the frame. Okay, maybe it's really too ugly. Okay, I think I draw it too ugly. Let's draw it like this, because then it's a bit more convincing. It's a little bit less wrong. So it is difficult to deal with this in the laboratory frame. What is the laboratory frame? You're in a fixed frame, and you look at two particles, and they, for example, both of them come kind of from the left, so they will leave out on the right? So, to make our life easier, what we can do is to go to a center of mass frame. Center of mass frame. So, what will happen in the center of mass frame? When we are in the center of mass frame, then, so the average center of mass, the average between the velocities of both particles, what will always happen is that particles then collide head-on, right? Yeah, because only their difference in velocity counts. So they will always collide head-on, and they will always go out how should I say, tail off. What is the difference between head-on, tail off? I don't know. Yeah. So they come in as f. Not f. They come in with the velocity xc1 and xc2, and they go off with xc-1 and xc-2. Now, what is already kind of indicated, and sorry for making this not absolutely drawing this picture not completely correct, but these collisions are derived under some conservation laws. So, question: what does the collisions like this actually conserve? There's one thing that is so obvious that it's kind of not no longer obvious.
Momentum.
Yeah, there is something more. The momentum is correct. So when so this is, I put this, it's third in my list. So what is so obvious that everybody forgets it is the number of the particles, right? So there are two particles coming in, two particles going out. So there's the number of particles. Oh, what I'm writing. What is also conserved even before this is the mass. Obviously, I mean, this is, when we do not distinguish between the particles, then they both have the same weight, unless we regard they in different groups. So you conserve the number of particles, you conserve the mass. Yeah? And then comes, of course, your momentum. But what would also be conserved is, of course, the angular momentum, because it has none. Yeah? Because they are going head-on, so there are no angular momentum. Zero angular momentum in, zero angular momentum out. Angular momentum. And then, of course, energy. So now energy is, of course, conserved in this setup. So what does it actually mean that momentum is conserved? So we have the mass of a particle and we have the velocities of the incoming velocity. So they two, both, that's what I'm writing, so the two of them together have a common momentum, right? And the outgoing momentum is the same. Even though probably in my picture it is not correctly drawn in the one on the left, yeah. So the momentum that is leaving is the same. So this is what momentum conservation means. Then we have energy conservation. So energy conservation is, okay, so there's again the mass of a particle, and now we have the energy. The energy is the square of the velocity, right? So this is the energy of particle 1 coming in, plus the energy of particle 2 also coming in, and all of this must be equal to the energy of the same guys going out. So this is 1, 1, 1, and there's a dash, plus 2 dash times 2 dash. So this is what we know. So now comes the ingenuity of Boltzmann with what in the Anglo-Saxon world is called molecular chaos. It's a funny thing because Boltzmann, of course, did not call it like this. There is a nice German word for molecular chaos, which is not a very verbatim translation actually, and this is called the Stoßzahlansatz. Okay, now you studied in Germany. You should always insist this is the Stoßzahlansatz. Yeah, it's like so. The Stoßzahlansatz is basically, so I mean it's more intuitively. Actually, the German term is more accurate description of what is actually happening. Yeah? So Boltzmann just said, so the idea behind this is that the dynamics can be reduced just to the number of collisions. You know, we are in a statistical world. Yeah? So all we need to know is how many collisions are there in a certain time, in a certain space. This was his idea. Yeah? So reduces, all the molecular dynamics reduced to the question, how many collisions are there? And I mean, there is one, even though I'm running a little bit in time, but there is one very important thing to get out of this. By taking the Stoßzahlansatz, we kind of disregard how this collision actually came about. Right? So we only count them. And by just counting them, we completely get rid of an accurate description of forces. Right? So we don't care whether they are van der Waals forces, other forces, or how these forces actually look like. We only count the number of interactions. And if you think about it, this is what we call physical kinetic. And now just think a little bit on your mechanics, and the irony a little bit behind this, where kinetics is in mechanics is the relationship between forces and change of momentum. In the real physical kinetics, forces disappear. There are no forces in kinetics. And go to your mechanic professors and tell him or her that in kinetics there are no forces. Then he tries to throw you out. But this is the reality. Yeah, there are no more forces. Forces are just gone. So, what we have to assume for all of this is that the colliding particles don't know about anything of each other. So particles are uncorrelated. So they don't know any, before they meet, they don't know anything about each other. Yeah? So we just count their collisions. So that means that the velocity, by the way, this is not completely correct, but it is it's asymptotically correct. So this is a starting point for a theory. It is, so to speak, the error that you make by assuming this is so incredibly small that it can be ignored. But if the number of particles is getting very, very small, then it can no longer be ignored. Yeah. So there is, you can only do statistics if you have enough individuals, and if the number of individuals becomes too small, then this can no longer be done. Okay. So particle 2. So what for practical reasons we are now going to do? And I said, we put ourselves in a center of mass frame. Yeah. We put these things in a center of mass frame by parametrization. With a direction vector. With a direction vector. They we call sigma, and all we demand of this direction vector is that it has length 1. So direction vector means it's a kind of unit vector that goes in any direction, right? And it has a length 1. So because this, we now can write the new velocity xi as the center of mass of the incoming velocity. Obviously, the center of mass does not change, right? So this here is center of mass. So we agree this is center of mass, obviously, right? And now there is the difference in velocity, and it's only so the only thing that causes the collision is the difference of velocity between the two, yeah, not how the entire universe around it moves with them. So we take the not the norm, what is the word? The absolute value, yeah, of their difference. And so we start with a vector. We want to have a vector again. Of course, we give them a direction, yeah. So because the outcome, right? So this is always true, but you don't know in what direction the particles go once they met. So they go in any random direction. So all of this here is now known, but we don't know sigma, because sigma is just random. Yeah, could be anything. So, but then the particle goes in this direction, and the other particle that was involved in the collision, which is the particle that was at velocity 2, this of course takes the same center of mass, and in the non-center of mass direction, it just goes in the opposite direction. So then I've miswrote this again. This must be minus, obviously, right? So now the two of them are just going opposite direction. Okay, so this is what always happens. Now we look at this collision integral, the collision operator, which is the difficult part in the Boltzmann equation. Because now we have to decide what actually is a collision. So how do collisions actually happen? Right? So in this somehow there are the forces. Yeah? Somehow hidden in this there must be the forces. So the collision integral, we call this thing omega. What is omega? Omega is the change of the state, the velocity state in time of the particle 1 due to collision. I mean, there's also a change due to the long-range forces, and then there's a change due to advection. Yeah, but this is the change due to collision. And now we get into having, let me see, what is the usual timing until for this lecture is 11:15, right?
Yeah.
Okay, okay, then I have to get a little bit speeding up. Yeah, so now comes the big integrals. I'm a little bit sorry for the big integrals. Now we sum over or integrate over all directions. So we take here a large sigma. Capital sigma means all directions, all possible directions. We're doing statistics, right? All possible directions. And we integrate over C2. Now I hope I'm not confusing you with the Greek letters. So the first thing is a capital sigma and the second is a capital Xi. So this is all the directions of the second velocity. So, yeah, so you could collide with all the other particles. So you're looking at particle 1 and now you are integrating over all possibilities that it meets a particle 2, right? So over all of them, then there is a so-called collision kernel. This is the thing that depends on what are the forces, what are the size of the particles, and so on. And this could also depend on the direction. Okay, could depend on the direction. Don't go into a lot of detail. And now this is a long integral, and this is why it doesn't fit in a single line. So I have to go to the next line. So there's multiplication. I go to the next line, and I start here because it's going to be long again. And then there is now two particles are meeting, right? So particles going out as the result. And now this is related. So there can only be a collision when there is a probability of two particles being in the same place, right? So their joint probability is the multiplication of the two probabilities. And because there's only two particles always colliding, it's only the probability between two particles. Yeah? And now this is the result, so the post-collision, after collision term. Yeah, and this is what comes out of the collision. So this is why it comes here positive. Yeah? This is what we call a gain. Gain is particles moving in this position, yeah, in this state. The state, again, here is the chairs in the room. Yeah? This is where somebody takes their place. And then the opposite, there is a removal of particles. So particles going in, colliding, they are in a certain state. When they collide, they are going out of that state. Yeah? So first term is they are going into that state, and the other is going out of the state. The one that is going out of the state, this is of course the pre-collision term, so there's without the dash. But it's the same problem. Yeah? There's the two of them colliding. So it's it's the product of both of them, and because they go out of the state, they are removed, so this is why they have a minus, and this is why we call this the loss term. And now we have to integrate this over the velocity xi2 and over all directions sigma. And this makes this collision integral. So the collision kernel B is a function of the relative. I mean, in a sense, it's also a function of how the molecules look like, but this is not what we mean here. It's of the relative velocities and the direction. And it's not a function of xi. So then gain is particles moving into, or we say scattered, yeah, because by collision they are moved into the velocity state xi1, and loss is particles scattered out of the state xi1. So now this accepts some conservation laws, obviously. So the collision should not destroy or generate energy or momentum. Yeah, this is what we have to take care of. And this can be done, so the collision integral conserves mass, momentum, and energy. The conservation of angular energy is somehow implicit to this. Okay, so this can be seen when we integrate over all outgoing velocities. Now there's an integration over xi1, the previous was over xi2. So we integrate the collision operator with a kernel function. This is different from the collision kernel. That is a function of xi1, and integrate this again over all xi1. And this phi would be an element of 1 xi1 and xi1 times xi1. So the thing is, the first, if you just integrate over all collisions, you get the mass that it's generated by the collision. If you integrate, if you multiply with the microscopic velocity and you integrate over all possible collisions, you get the momentum, yeah, the velocity, or yeah, the momentum generated by all possible collisions, and this should be 0. And if you multiply with the velocity square, you get the energy generated by the collision, and all of them should be 0. This is why this here is 0. So, and this kind of thing here, which may not be very familiar to you at the moment, will hopefully become more familiar to you during the lecture, because this is very important in kinetic theory, where we work with so-called moments. I mean, maybe in statistics you've learned about moments, right? Okay. So the integral of a distribution f with a kernel phi is called a moment, and they are more or less the most important entity that we have to understand in order to understand kinetic theory. So, okay, I'm going a bit quick on this, but all of this we'll discuss a lot during the rest of the lecture. I'm introducing it, and don't be afraid if now it still looks a bit confusing. Will become very clear later. This collision obviously has 5 conserved moments because velocity has 3 components. Energy and density have only 1. So there are 5 conserved moments. And actually these conserved moments correspond to the primitive variables in continuum theory. So the primitive variables in continuum theory are particularly the velocity and the pressure, right? And maybe the temperature. So so the moments, this is why they are so important for us, yeah, because the moment we take statistical moments in kinetic theory, and then we see that the moments obey the partial differential equations that we already know about before we invented kinetic theory, right? So, and you see, what is coming out is, for example, the density, rho is just the integral over xc1 over f over all velocities xc1 dxc1. So this is what we call the zero moment because nothing goes in. Then there is velocity u. So there's a little bit of a problem because in order to actually get the velocity instead of the momentum, we have to scale the distribution. Yeah, this is what I mean, you can define different moments getting different results. Yeah, you can define a moment as being the momentum. Never confuse momentum with moment. Yeah, if we have fc1 times the velocity xc1, and we divide this by rho, by the density, right? So then we actually get the velocity, because I wanted to go to the primitive variables. So you can also design a moment without dividing by rho, then we would end up at the momentum instead of the velocity. Okay, and what also drops out in a little bit more complicated way is the temperature T. That would be an integral. So you see, it's getting a little bit more involved here because this is kind of related to the center of mass velocity. So we take the macroscopic velocity out, yeah, and just we put us in the moving frame of reference, and take the square of this vector by taking the scalar product with itself, and we divide by rho and the number of dimensions. So this is actually 3. Yeah, so d is equal to 3 number of dimensions. Okay, now I just can't take it without introducing the so-called H-Theorem. And in principle, okay, I started late. This is why we have now only apparently 10 minutes left. And some people consider this a bit complicated, and maybe you say it was already complicated. so I want to present it to you because it's kind of important, and maybe you know, maybe it is. I mean, it is important for the way we understand the universe today. But most people think, okay, some physicists figured this out and just give me the result, yeah. But I just find it so important that you should at least have heard this once, and then you can decide whether you go look at it again and try to understand it, or you just accept the result. Okay? But anyway, briefly do it. Okay, so this letter, it already starts to be confusing with the fact that the letter looks like an H, but is a capital ether. Yeah, so it's called the ether theorem, and some people call it the H-Theorem because they don't know better. So the ether theorem is important for us to understand the direction of time. Actually, this is how Boltzmann showed that the universe goes in a certain, it changes in a certain direction. By the attempt to understand what would be the state where nothing else changes, which we call the equilibrium state. So you see, we have introduced the loss term and we have introduced the gain term. And now the question is, what is dominant? What is happening? And there would be a place or a time when loss and gain are in balance. And this balance we call equilibrium, because it is equilibrium. Everything is kind of the same. No, I'm talking nonsense, sorry. So, what it actually means is that gain and loss are the same. So, this is the place where nothing else happens. Yeah? So, then the distribution obviously do no longer change. It does not change anymore. And then this is what we call the system is in equilibrium, because it does not change unless we put external energy into it. So, what does this mean for our collision operator? Now I am deciding there is an equation 1.1, and we look at our collision operator dfxc1 to time for the collision only. So the collision operator, there is a b that is a function of the difference of the velocities, and this goes into the differences. Now we know this is equilibrium. So this is again the gain term minus the loss term. So, and no, without dash, obviously. Without dash. And this goes over the C2 and over all directions. So now what I did here is I defined F1 as being Fc1 and F1 dash as F, so this definition to shorthand this, as F of the velocity C1 dash, right? So we are going to understand this. So now Boltzmann defined a function ether It's absolutely not clear how he came about this, but now he just did so. He defined the function ether to help him identifying the equilibrium. So this was defined, so this is a function of time, as an integral over the n, so actually it was a double integral, an integral over f1 times the logarithm of f1, so this is how you defined this, over all the velocities, and this is important, over all spaces. So there's an integral over the universe, yeah? An integral over the universe. Integral over all micro velocities, velocities, and all coordinates. That is the universe. So there's nothing external to this anymore. So now what we do is we take the time derivative, or this is what Boltzmann did, we took the time derivative of this guy and we drag the time derivative into the integral dt f1, the logarithm of f1, and we integrate this so again. So you notice what I did. I just dragged the time derivative into the integral, and now I execute this and see that this, or I distribute it over what I have here. So I have the time derivative of f by t, which is the collision, and then I apply the chain rule. No, not the multiplication. What's called multiplication rule? So I first have the logarithm of f1 stands here, and then again the other part is I let f standing here, and then the derivative of the logarithm is 1 over f, which gives me plus f1 divided by f1. So, and I think that Boltzmann wanted to obtain this result, so he devised a function that gives him this result. Yeah, but otherwise I don't know how he came about this. So this, by the way, is C1. So, and this over all the space. So now here you identify obviously the collision operator. So now, what is the H-Theorem? The H-Theorem is the observation, is actually a mathematical proof. This is, I mean, if everything we assume here is correct, then you can prove that the time derivative of this guy is smaller than 0. And the equilibrium is the state at which it actually is 0. Yeah, the time derivative is 0. Okay, nothing changed. Time derivative is 0. So it makes sense. Now, I'm going to take some overtime, but I'll do it anyway. I give you the answer why this is smaller than 0. Are you interested in this? Now, you came here, I hope you are. Okay, so let's put the collision operator. So we identified that in 1.2, there is the collision operator, yeah? So let's put the collision operator into it. So this gives us equation 1.3, ether by dt. Now collision operator comes in. Okay, for simplification, I will now only write one integral sign. Otherwise, we were getting more and more and more integral signs. Yeah, and I don't put the range here because we always integrate over everything. Okay, we can agree on this. So there's b f1, f2, gain term minus loss term. And this comes now into 1 plus log. So 1 is f divided by f, obviously, log f1. And now this is integrated over xi1 and xi2. So the xi1 and the xi2 comes from the collision operator, and the xi1 comes from the integral 1.2, obviously, right? And this again over the r, and actually in my notes I've forgotten to write d sigma, because this is also in here. Okay, so this is now the equation 1.2 with the collision operator put into this, and here you see this is a function of f1. But the entire thing should be independent of whether we regard particle 1 or particle 2, obviously. Or yes, so and this is why f1 and f2 should be interchangeable. Yeah, so the one particle does something, is doing more or less is doing the same thing to the other particle than the other particle is doing to the one particle. So they are both interchangeable, and this means we can write a similar, completely similar equation, 1.4 d ether by dt, where all we do is replacing f1, and so here it does not matter, but here we get the logarithm of f2 instead, right? So it should be the same thing. And we integrate again, so I'm not going to exchange these things here. We integrate over both of them, over all directions, over all spaces and all directions. Now, very simple, we can sum the two guys together. 1.3 plus 1.4, yeah, gives us 1.5. Okay, that was not a mathematical equation, right? So d is by dt 2. So on the left-hand side we have two of them. Then we integrate bf1 dash, so the gain term again minus the loss term. Now here we have 2 plus the logarithm. So how do we add up logarithms? We add up logarithms by taking the product of them, right? Very simple. And then comes the integral over everything again. And now we do another exchange. And this is kind of important and funny. Namely, we say that the collision is a symmetric operation. Yeah? So whatever comes in, so whatever happens in one direction can go in the other direction. And historically, this is a very important thing, because in the 19th century, it was always, I mean, the way of thinking is everything is reversible. Yeah, the equations of nature are symmetric, so you change the direction in time, you change the velocities, everything will go backward. So this is exactly what was this state of thinking, and is still true, of course, in the 19th century. So complete agreement on that thing. Now, we assume the collision to be symmetric, and so it can go forward and backward. And this is very, very important to take this, to keep this in mind. We are assuming that the universe is time symmetric. Physics is time symmetric. This is the assumption that we put into it, right? It's time symmetric. And when it's time symmetric, we can exchange the preverse or the outcome with the input. This can be exchanged. So what happens if we do this? Then we have 2 times the derivative of eta is equal to integral over b f1 f2. Now loss and gain have changed spaces, and the difference here is now that the logarithm goes over f. The outcome of the collision, and again this is integrated over everything, and sigma. Oops. So now what we do is we add forward and backwards together. We add forward and backward together, and now we have 4 times the derivative. 4 times the derivative is again the integral b. Now you see that there was a change in sign by them, but I will write this now. Oh my God, I miswrote this. So let me try to correct it ad hoc. I had this. Okay, let me try to correct it ad hoc and see whether this is now correct. So we have the original gain term minus f1 f2. So, and now comes the part from equation 1.5, which is this one. You see, because the sign in this part here has changed, the 2 will disappear from both equations, yeah? Because we multiply with the opposite. So we'll now get from the equation 1.6 minus the logarithm of f1 f2 dash, and now all of them integrated over everything, the r, the sigma. Okay, and this hopefully, yes, okay, so this hopefully is smaller or equal to 0. Do you see it? Why? The logarithm is monotonic. Right? So this means that if f1, f2 would be smaller, or the same thing goes when it's larger in the opposite way. So if this is smaller than that, then the logarithm of f1, f2 is smaller than the logarithm of f1 dash, f2 dash. Okay. So, which means that in this integral, there are 2 parts. That one and that one. And when one of them, I mean, there could be 0, right? But otherwise, if one of them is positive, then the other one is negative. Always. Everywhere. And now you integrate it. So it will always, this thing will always come out negative. Which means that ether, the time derivative of ether, will always go into one direction. And the fun part of this means that the development of the universe, because we are talking about the universe, is not time symmetric, right? So it goes, or it's not even not time symmetric, but it's just going one way, right? The evolution of the universe has a direction in time. And the fun part of this is that we derive this from the assumption that the individual collision, that the individual event in physics is symmetric. So if each individual event is symmetric, time symmetric and reversible, then the universe is irreversible. And this is the ether theory. So this tells us where time is going. Okay, now we are so much over time that I'm going to just finish this with these two sentences that I still have. So ether provides a direction of time. So I'm writing down what I just said, from the assumption of reversible collisions arises the irreversibility of the entire system. Okay, so with time, the system goes always closer to equilibrium. So dH dt. So equilibrium is where this is zero, and this ether is actually identified as the scaled negative entropy. So, sorry for being long. I will now stop the recording.